In this video, we are going to be calculating equilibrium constants. Now, you should have a good understanding as to how to write an equilibrium constant expression, what to include in an equilibrium constant expression. So we are going to write the equilibrium constant expression for this reaction. We have H2 reacting with I2 to give 2 moles of HI. So I'm going to put this in terms of concentration because I know that later on I'm going to need it. So we have the Kc is equal to Hi, these are the products, squared because the coefficient is 2 over H2 times I2, and those are all in concentration units. Let's say we have a mixture and we have the ingredients of 0.5 molar H2 and 0.5 molar I2, and we allow it to come to equilibrium at 445 degrees Celsius. The equilibrium concentrations of each of the chemicals are, we have 0.11 molar H2, 0.11 molar I2, and 0.78 molar HI. So what is the value of the equilibrium constant? Well, what we can do is we have this initial mixture of H2 and I2. Now, notice we don't have any products. When we allow it to come to equilibrium, we still have some reactants left over and a lot of products. So if we put this and we substitute these values into our equilibrium constant expression, then basically all we have to do is a little bit of math, and we can find the equilibrium constant for this reaction at 445 degrees Celsius. So 0.78 squared is my concentration of my hydrogen iodide, and that's over 0.11 times 0.11. So 50 is the value for our equilibrium constant. Let's take a look at this exact same reaction, but we're going to start with a new mixture of 1 molar H2 and 0.5 molar I2. We allow this to come to equilibrium at the same temperature, and the new concentrations of each chemical at equilibrium are H2 is 0.53 molar, I2 is 0.033 molar, and the HI is 0.934 molar. So we have different equilibrium concentrations because we started with a different mixture of ingredients. We had different quantities of our ingredients. So we're going to plug these numbers into the same equilibrium constant expression, do the math, do the multiplying and the dividing, and what we end up with is 50. So what you can see, that new value of the equilibrium constant, you can see that no matter what, the equilibrium constant has the same value. The things that were different were the initial and final concentrations of each ingredient, each reactant, and each product. The equilibrium constant remains the same though. So the equilibrium concentrations of the reactants and products depend on the initial concentrations, but the equilibrium constant will always be the same. So what do we do when we are not given explicitly, we're not given those equilibrium concentrations? Well, there's a few things we can do, and a lot of it will have to do with the stoichiometry, the coefficients of the reaction. So we're just going to start with a simple, not even a real chemical reaction. A reacts to give B. And we're going to see that we have an initial concentration of A is 1 molar, and the initial concentration of B is 0. We have no products. And we know one piece of information about our equilibrium concentration. We know that the concentration of A is 0.75 molar. What that means is that the concentration of A went down by 0.25 molar, which means the concentration of B had to increase by 0.5 molar because the coefficient of B is 2. So what is the new equilibrium concentration of B? Well, that's 0.50 molar. So now we have enough information to calculate out our equilibrium constant. Here's the equilibrium constant expression, which is B squared, because the coefficient is 2, over A. So I will substitute in my equilibrium values. So the B will be 0.50, and that will be squared because the coefficient for B is 2, and that will be over my reactant A, so 0.75, and that will equal 0.33. So my equilibrium constant is 0.33 for this reaction at that temperature. So one thing that we are going to be using a lot of are these ice tables or ice boxes. We start with our reaction. We need to know what the reactants are and what the products are, the initial concentrations of everything, how much each changes, and then the final equilibrium concentrations. Let's take a look at a practice problem with real chemicals. So we have this reaction here. Methane turns into C2H2 and 3 H2s. So I'm going to write the equilibrium constant expression. So we have C2H2, or the concentration of C2H2, times the concentration of H2 cubed, because the coefficient is 3, over the concentration of CH4 squared. Now, the reaction mixture at 1700 degrees Celsius initially contains 0.115 molar CH4, and at equilibrium, the mixture contains 0.035 molar C2H2. What is the value of the equilibrium constant? So I'm entering in my initial values. I started with the reaction. I'm entering in my initial values, and then the final value that I know. I can use this final value to figure out everything else because I know that I'm gaining 0.035 molar of the C2H2. So I'm going to look at the coefficients now, and I know that I will gain 3 times as much hydrogen. So that's 0.010 or 0.105 because the coefficient on the hydrogen is 3. What that also means is that I will lose twice as much CH4. So 0.035 times 2 is 0.07. So I'm going to subtract that from my initial concentration of the CH4, and I get 0.045. So these are all of my equilibrium concentrations. Notice how the change in concentrations were negative for the reactants and positive for the products, and we used the coefficients of the equation to figure out how much each one changed. So I plug all of these equilibrium concentrations into my original equilibrium constant expression, and all I need to do is just type in some calculator numbers, and out pops out 0.020 for my equilibrium constant. So what we need to be doing here is setting up these ice boxes. ICE, initial, change, and equilibrium. We need to start with the reaction, figure out what the initial concentration is, the change, and then the equilibrium concentrations.